Okay, I wanted to go over a problem and setting it up and illustrate how we can set up this problem. And specifically, there are various ways we can set up problems and the variables that we use when we are solving these material balance problems. And I want to show you 3 different ways that we can go about doing this. And the first one is a technique that we've been using quite extensively in class, and shouldn't hopefully be anything too new to you. But the way we set up this problem is we go ahead, in this case we know everything about this stream and we know everything about this stream. This is a 2-component problem. A and B are 2 components. We just don't know anything about this stream. It's an unknown that we're trying to solve for. And what we can do is we can go ahead and define a flow rate of that stream. We can define a mass fraction of A, mass fraction of B, and this gives us 3 variables that we're going to try to solve for our 3 unknowns. So we have our 3 unknowns here, so we need to write out 3 equations to be able to solve it, and we typically have been writing material balances. Since we have 2 species, we'll write out 2 material balance equations. I can write out my total balance. That's my total balance right there. I can write out a balance on A. Let me just write this here. So that's my material balance on A. The third equation that I'm going to use is 1 is equal to WA plus WB. And so those are our 3 equations that we're going to use, these 3 equations, to solve for our 3 unknowns. And this is what we typically have been doing a lot of times in class. So that's our first method. Let me go ahead and erase this here. And show you a different method that we can go ahead and solve this. And this is our second method that we can go ahead and solve this. And it's much like the first method, it's just how we set up our variables. In this case, what we could do is we could just simply call this M for the flow rate, and we'll call this WA, and then we'll for flow rate of or the mass fraction of species A, and then 1 minus WA, and in this case this is the mass fraction B. So we have, in this case, we only have 2 unknowns. We have mass, flow rate, WA, and then 1 minus WA. And in this case, we'll write out our 2 equations here. So I have 2 equations that we'll write out, our 2 equations coming from material balance, and our total again, 100 is equal to 45 plus M. Our balance on A is 100 times 0.5 is equal to M times WA plus 45 times 0.3. So that's our material balance on A. And then you say, well, what about our third equation? 1 is equal to WA plus WB. Well, we don't have to worry about that equation because right here we've already taken that into account. This equation, by using 1 minus WA here, that already takes into account this equation here. So we don't have to include this equation when we're solving the problem because it's already taken into account right there. So in this setup, we just have two unknowns and then 2 equations we have to worry about. And so we just define, rather than defining WA and WB, we just define this second variable as 1 minus WA. So that's the second method. And let me go ahead and show you the third method. So let me just show you one other way that we can go about solving this problem. And this is the third method. And the way that we solve this problem is we define variable M for our total flow rate, MA, MB. So in this case, our 3 variables are not necessarily in terms of mass fractions, but instead we're defining this as total flow rate of A, flow rate of B. And we're just ignoring our mass fractions. We can go ahead and calculate mass fractions in the end after we already solved the problem, but the way we'd set this up is we'd have to, in this case, we would write out our three equations. Two of those are material balance, since we have two species. And in this case, 100 equals 45 plus m is our total balance. Our second equation is A balance. Let me just write that out. 45. And in this case, it's MA, so that's our second equation. Now, you may think, well, let's write our third equation be our material balance on species B, but remember again, when we have two species, only two of those equations are independent. So our third equation is just simply M is equal to MA plus MB. So that's our third equation. And so looking at this, we have three equations, 1, 2, 3, three unknowns, and we can go ahead and solve this, just do some algebra and some math, and we get the solution to this. So just in summary, I've shown you three different ways that we can set up the problem. We could define mass fractions for this particular stream, where we have WA and WA and WB for our two variables. We can have our second method, which was WA, and then the second variable was defined as 1 minus WA. And then this third technique is we just simply define flow rates for species A, MA, and MB. And we could write do a similar analysis if these were mole fractions or mole flow rates. So instead, if this was all in terms of moles, we could go ahead and write out similar equations instead of in terms of mass or mass fractions. But the point being, there are different ways that we can solve these problems. And depending on how the problem is set up or given to us or presented to us, we may want to do one of these alternative techniques. We may sometimes want to solve it in terms of flow rates, or we may want to solve it in terms of mass fractions or mole fractions if it's given to us. So again, different ways that we can set up a problem and eventually solve it.